Hello and welcome everyone. I'm happy to have you here at our webinar, Steam and Power Optimization, Superior Management of Steam Networks. Just a little note before we start. On the right-hand side, you can see a screenshot of your interface. You can submit your questions also here on the webinar via the question and answer box. You will be all in mute mode, and today's presentation will be recorded. The following question and answer session will not be recorded, and the recording will be provided to you for your reference. So a little disclaimer at the beginning. The information in this document is subject to change without notice and should not be construed as a commitment by ABB. So, welcome. Today we are presenting our outstanding solution on steam and power optimization for superior management of steam networks. On the panel today with me are Riccardo Martini and Francesco Giotto. Welcome, Riccardo. Can you introduce yourself, please?
Yes, thank you, Sleman. Obviously my name is Riccardo Martini. I belong to the Optimax product management team. I'm responsible for ABC module product management for the energy industries in ABB. My background is in petrochemicals and refining, especially around cogeneration. And I've been working in that field for ABC and energy management for the past 20 years, roughly.
Thanks, Riccardo. Welcome, Francesco. Can you say a couple of words about you, please?
Thank you very much, Sleman. My name is Francesco Giotto. I'm in ABB since 10 years. I'm a chemical engineer as a background, and I'm in the energy industry division, and my main area of expertise is in advanced process control, real-time optimization, and in general process optimization.
Thanks, Francesco. For the last speaker, my humble self, I'm Sleman Saliba. I'm the Global Product Manager for Optimax. Safety moment. Probably most of you are listening from home and are familiar with the surroundings. Nevertheless, please always obey your local safety rules. And this applies especially when attending this tech talk while driving a car. And also, please obey to the local COVID rules and keep social distance. Yeah, but let's get started and jump right directly into the topic. So when we talk about steam and power optimization, Riccardo, what are the challenges that our customer face when operating in industrial sites, and for which industries is this applicable?
Well, first of all, let's take a look at our case, and we are talking about industrial processes where we have steam and power demand, and there's typically one process side, and there's also a utility side, and the distinction in some cases could be a little bit blurry as there are energy recovery units and energy recovery equipment as well. And what is that we see? First of all, we see that we have a complex control and optimization problem as we have several interactions. So first of all, on the steam level to keep the pressure stable. And also we have interaction between steam and power in general for each of the subsystems. And we also have interaction with the external grid in order to keep a frequency stable, we import or export sufficient energy to keep that stable. And what is that we can say that first of all, the problem is site-wide as as these networks cover the entire sites. And any big disturbance on the steam network, for example, will have an effect, an impact on the entire site. So the coordination must be from a global perspective. At the same time, we see that steam and power production is a significant contributor to the site operation costs, but also that typically, and for obvious reasons, the process has priority over utilities. This has some impact as in practice, the need to compensate the disturbances coming from the process side may have a cost impact on the utilities that it's not always fully calculated and understood. What are the relevant industries? Well, first of all, certainly oil and gas, refining and petrochemicals, chemicals, industrial cogeneration in general, and also applicable to district heating networks. More in general, also paper, food, metals, and minerals.
Thanks, Ricardo. So you talked about industrial sites or utilities that have on-site power generation, that have steam generation and have the need to reduce energy cost and primary fuel cost. And all that is also coupled with energy markets and different prices for primary fuels. So Ricardo, with your expertise, what's so complex about coupling industrial steam and power networks that you started in the first two slides?
Yes, first of all, let's have a look at the technical challenges in steam and power control. Well, first of all, we have multiple equipment with different efficiency, different sizing, and very often different age. Moreover, there's typically a conflict between fast and slow dynamics, and there are some slow equipment like typically boiler and heat recovery and steam generators. And we also have fast equipment like, for example, turbine or pressure reduction valves, to give a couple of examples. Well, further complexity is also related to steam and power demand changes and variability on the demand. And also energy recovery related disturbances, like, for example, energy recovery in terms of steam, like, for example, from a steam cracker, or in terms of a CO boiler or off-gas availability. And also, I want to mention that there could be steam and power related events, like a trip in a turbo pump or in a turbine, which will have an impact on the entire steam network. Also, worth mentioning, changes in fuel availability. So, for example, if you are using fuel oil in the boilers that it's coming from the process side, we may have to keep a tank level in a certain range, and that has an impact on the availability of a certain boiler for load changes. And finally, and you anticipated that in your questions, there's a impact on our management from the variability on the energy market, as prices can change significantly, especially in these days, and that should be taken into account. What are further challenges? Well, first of all, steam and power, as we said, are strongly interconnected. So we would like to have a global management. So some kind of strategy in the automation layer, which takes care of both, considering their respective objectives. Well, there are some practical hurdles. For example, there are typically different automation systems, typically different control rooms and different organizations involved. Sometimes there are even different companies that are taking care of the process side and the power side. But at the same time, what we can say is that there are opportunities. For example, and this is just an example, trade-off between power and steam are often possible. For example, it's possible to use boilers as power boosters to help generation. And depending on energy price and fuel costs, optimal condition change. So it's not trivial to understand what is best without considering the entire steam network. And a coordinated control would give us explicit economic benefits with tangible potential savings or additional revenues. Let's dig a little bit further on what are the benefits from a coordinated control. Well, first of all, turbines have different efficiency curves. They could be very different between each other, and there's also typically an optimal operation range for each of them. Boilers as well, they have different efficiency curves and also may use different fuel types, which can make a calculation of the optimal efficiency interesting and more complex than one would assume. And you can also consider the contract type and, for example, take into account fuel blocks when doing these calculations, so that we actually implement what's best from an efficiency and also from a financial point of view. It should be mentioned the optimal balance cannot be calculated only once, but it should be continuously performed as the balance keeps changing. Firm motivation for coordinated control are related to minimization of possibly a complete avoidance of venting. Venting is a easily spottable area of improvement, as it is certainly loss efficiency and loss of money. But at the same time, rapid pressure swings require some control, and unless you have a coordinated control of multiple equipment, you end up venting more than necessary. So that's an area of interest. Another area of interest is use of pressure reduction valves, as pressure reduction valves are basically bypassing turbines, so they have a negative effect on efficiency, and they also have typically a negative impact on the financials. And there are cases when the energy prices are particularly low, where it's interesting to use the pressure reduction valves and a temperation, and we will see that in the demo. But I want to mention that the use of pressure reduction valves should be based on an economic decision and not just because it makes easier to control the steam network pressures. Condensation similarly could be beneficial or could be bad from an economic standpoint. Typically, it's more of the second case, especially if you're using conventional boilers or you're using post-firing to produce the steam. Also, there's an opportunity to optimize steam header pressure and temperature control, so to make sure that we get the right pressure and right temperature to all the users, and we minimize the variability on the headers. Also, and we talked about this already, interaction with the energy market and being more active in this area. This is of particular interest in these days, as there's more and more volatility on the energy prices, and there's also more volatility on the frequency control, thanks to environmental friendly power producers. Last but not least, coordinated control should also have an eye on emission limits, as the emission limits are typically associated with the average over a longer time horizon between 1 hour, 24 hours, or 1 month, depending on the local regulations. And this is not easily something that you cannot easily keep an eye on from a pure automation perspective. And also CO2 economics, as it's getting more and more, I would say, necessary to keep an eye on those costs for especially in Europe and in Americas. So let's have a look a little bit on the technical solution that we have identified to resolve that. Well, first of all, the idea is to have a coordinated control of steam and power using a standard software solution based on ABB Optimax software. The idea is to use 2 layers. The first one is based on an optimizer, which is able to calculate the optimal operating point considering nonlinear models and explicit economics. And with explicit economics, I mean also considering fuel cost and fuel contract types, and also having the ability to estimate the energy export or energy import related costs. So, the type of market and the type of cost associated with changes from that perspective. And then a second layer featuring a steam coordinated based on model-based predictive control technology, typically called APC, which can drive the plant toward the optimum operating conditions while at the same time preserving steam network stability. I want to stress that steam network stability and quality of the steam on the network is our most important target and as a priority over the financials. But when the steam network is in stable conditions and all the targets are close to their set points, all the variables are close to their set points, then the software will pursue explicit economic benefit for the overall site. And this is provided by a single solution based on Optimax platform, which covers the two software modules that I just presented. And overall, it has a standard OPC interface based on DA and UA technology. This means that it's applicable both to ABB and non-ABB automation systems. Let's dig a little bit further on the technical benefits. Basically, this solution can provide automatic control of short-term and long-term control objectives. And with short-term, I mean, again, steam pressure and steam temperature control. Long-term, we aim targets that are a little bit longer, like in terms of time horizon, like energy exchange during the 15 minutes or during the 1 hour period, or whatever it is relevant for the market. It has also the ability to implement flexible strategies, multiple objectives, and their explicit priority and economic benefit and penalties, so that we can consider all the variables before making a decision. And the software solution has also embedded features for management of forecasting and energy management and energy market interaction. Real-time, intraday, day-ahead market, depending on whatever is relevant for the case. But the software has the ability and built-in interfaces to handle all that. It also provides a single HMI, a single console where you can supervise, monitor, and control an entire steam network optimization and also power control as well from a unique HMI, which is web-based and can be used by multiple engineers in parallel together with the operators. It also provides performance monitoring and tracking, which is always important, but it's particularly important for energy-related markets, where being able to meet whatever was promised to the market could be could make it a big difference in terms of penalties.
Wow, it looks complex, but when you explain it, Ricardo, it all makes perfect sense. Thanks. So you talked about the superior technical solution and its benefits, and we briefly touched on the fact that with steam and power optimization, customer can save steam cost, emissions, and all that with an attractive return on invest. Can you give us some details on that now?
Well, first of all, there are some direct benefits, and first of all, the increase in energy efficiency, which has also the benefit in terms of CO2 footprint reduction. Also, there's a production cost minimization, which we can provide by considering explicitly efficiency and fuel costs and fuel contracts and energy contracts together. If you are a net exporter or if you are actively buying the energy on the energy market, then you can be more proactive in your approach to the market, which means that typically more profits or lower operating costs. And the typical benefits in our experience are in the 3 to 5% of the total SIMS cost on average, with a very good return of investment well below 1 year. And I want to stress that the degree of return of investment and benefits, it's also strongly related to how much you can be active on the energy market, and could actually be significant more than that. There are also additional benefits, and the use of Optimax allows you to use the same models that you developed for runtime control, also for scheduling and planning of your decisions on the site, whether it is related to steam or it is related to energy. You can basically use your Optimax model for forecasting and also what if scenarios, and make sure, for example, that you get the right combination of boilers when you are planning your shutdown of certain process units or equipment. An additional benefit that it's worth to mention is as well, has to do instead with the real-time management, and it's coordinated, the ability to do coordinated management of steam and power related events. So for example, if you have a trip on one of the key equipment, or you even have a disconnection from the grid, and you have a complex load shedding, to take into account, well, steam and power optimization can take over steam control after the load shedding, and keep the steam pressure and steam temperature as stable as possible by moving multiple equipment at the same time. It is very, very well known that when you have a load shedding event, after a few minutes, after 10 minutes, there's a steam crisis, which takes a lot to be handled by different control rooms via telephone, acting on multiple areas of the process side and power side, and trying to keep the pressure as stable as possible in the steam network. Well, our solution can handle that automatically and reduce the events, and if they happen, mitigate them by moving multiple equipment in a coordinated way. Also, as a side effect, as we during the implementation, it is our experience that we normally find areas of improvement in the control strategies for boilers and turbines. And I'm talking more at the base level, at automation level, but that allows us significant tangible benefits. A little bit on the experience. ABB has experience on refining petrochem and chem sites, and also applying this technology also in cogeneration with integrated district heating, and paper, metals, minerals, food as well. And the experience from ABB is not only on ABB automation system, but also on third-party systems. Actually, in most cases, as it is a site-wide, it is a combination of multiple DCS systems, so not just ABB, but also third-party. It's kind of the typical case.
Thank you, Ricardo. And for you on the call, you can now see an exclusive demo of the system right now.
Well, first of all, you are going to see a full interactive demo with a simulation of steam networks, boilers, and turbines, and DCS logic via an 800XA soft controller. And the idea is that by having a soft controller, we provide an environment for simple simulation of the process and DCS logics. And then we will see a web HMI that will be used for monitoring and command of power, energy, and also steam. And finally, there's also an 800XA HMI for basic supervision of the application, but it's a kind of available in there, but you can use you can get full information from the web version.
Okay, very good. Okay, so as Ricardo was mentioning, we have a DCS layer in this simulation, which is using a ABB soft controller, which has a built-in functionality of 800XA to emulate a process and also DCS control logics. Okay, but I will not spend a lot of time on the DCS part, because as we are mentioning, we are using ABB DCS only because it's easier for us to simulate the process, but the solution works perfectly with any kind of DCS since it uses the standard OPC communication. Okay, so here you are seeing a DCS graphic display of the steam network that we are gonna deal with today. We have two pressure header, one high pressure header and one medium pressure header, 82 and 13.5 bars. And we have several boilers with different fuel types. So here on the right, you see the fuel types. So basically boiler one is oil fueled, and we have two natural gas boiler on the high pressure header. Plus we have an heat recovery from a steam cracking unit producing 119 tons of steam in this moment. And we have three steam turbines and one PRV connecting the two pressure headers. And in this case, for example, we are simulating as one turbine under maintenance, so that you can also see what happens when an equipment on the network is in maintenance. So you see that it's not the loop is in manual and is not producing any kind of energy. Plus, we have other 3 oil-fueled boilers on the medium pressure header, plus an heat recovery from process which is producing 21 tons of steam. On the medium pressure header, we also have 1 vent valve, and Ricardo mentioned in his presentation that venting in general in this kind of system is a net loss. And plus we have the users, so we have some high pressure users, but also most of the users are medium pressure steam users. So we have 760 tons of steam on medium pressure steam, and only 15 tons of steam per hour on the high pressure. Okay, so this is the overview of the network. As we are dealing, we can have a DCS displays, but I will not show you these DCS displays, since I think it's way better to directly jump into the Optimax web interface. So this one that I'm showing you is basically the web interface of the optimizer solution. As you can see, we have several tabs here at the top. The first one are to monitor and command, the first 4 of them, they are to monitor and command the steam coordinator. If you remember the automation pyramid that Ricardo showed you. And we have 3 tabs to monitor and command the optimizer. So this one is the overview of the steam network. So as you can see, it's possible also to replicate DCS displays on these HMI. And as you can see, we have for every boiler the current production in black, the optimal production calculated by the optimizer in green, plus the operating range of the boiler. Okay, so as you can see, all boilers, they have different operating ranges, but also different efficiency, and I will show you this in a while. And in addition to this, the optimizer is also reading the actual cost of the raw materials. So we have a fuel oil cost, a natural gas cost, and an electricity cost. So in this case, you can see that we have a very high oil cost, which is way higher than the natural gas, and a good electricity price. These are in dollars, okay? And we also have the steam demand, okay? So let's have a look at what happens in the monitoring tab of the optimizer. So here at the top, we have the production of every item in our system. And as you can see, they are pretty flat in this moment because the optimizer is in a mode that we call advisory mode, okay? So it's just calculating and suggesting the optimal load allocation. So let's have a deeper look and to I think with the most interesting graph in this demo. So here we have in this graph, we have in blue the calculated actual cost of production for the steam against in green the optimal cost of production. So as you can see, the two, they are pretty far from each other. And how far we are from the optimal solution, how far we are is represented by these bar charts here, okay? So these bar charts shows how far every item, so you see that we have boiler 1, 2, so all boilers plus the pressure relief valve here and the 3 turbines here. How far every item of our network is in terms of tons of steam per hour produced from its optimal allocation, okay? So basically we can see, for example, turbine 2 is 175 tons of steam per hour, far from the optimal load allocation, and the same for boilers, okay? So what we can do now, so in order to implement and to really optimize the system, what we can do is basically to switch the optimizer from the off mode, so only from advisory, to closed loop system. And when we close the loop, what does it mean? It basically means that the optimizer will start to move and to write set points on standard DCS loops. So if we go to the steam coordinator list of objective, you will see that here we have the list of the target for the optimizer, and if we have a deeper look, we can see that we have high pressure header and medium pressure header stability in terms of pressure control. We also have some constraint in terms of mass balances and also in terms of venting minimization, okay? And from PV6 till PV15, we have basically the list of optimal target calculated by the optimizer. And these targets from PV6 till PV15, they are at a lower priority, okay? So basically the main target for the coordinator is to keep the pressure of the header stable, okay? And how the optimizer can do this? So if we go to the list of the manipulated variables of the coordinator, we can see which set point actually we are writing on the standard DCS control loops, okay? So you see in the mode column, we have some equipment that are in auto and some of them, they are in manual. So for example, I mentioned in the beginning that turbine 3 was simulated in manual mode and was off. That's why it's not taking into account in this moment. And same was for boiler 6, which was out of service. Okay, so this is why they are in manual. So basically, these are the set points that our coordinator is writing. So let's go back for a second to the monitoring tab. And if you see immediately here at the top, you see that the production of the items is starting to move now that we are closing the loop, okay? And if you go down here, you will see that actually these bar charts, the number are slowly decrease because we are actually slowly approaching the optimal solution. And also you can see immediately that the actual cost of production is decreasing, okay? Of course, in this demo, the dynamics are actually faster than in a normal plant because, you know, we don't have too much time to wait for steady state. But of course, the coordinator always has an higher priority on pressure and try to optimize the system at a slower rate, okay? We can also do a couple of tests, which I think they are pretty interesting. If we go again to the overview tab, okay, I can show you what happens when you change, when you change, or actually this cost in a real plant, they will be read via internet or via PI system or via, for example, an energy broker for the electricity. Okay, so let's first see what changes if we make, for example, the oil cost less expensive. Okay, now we are the optimal solution would be, as you can see here, to maximize boiler 2 and boiler 3 production, and also to maximize the two steam turbines. Okay, so let's see what happens if we make, for example, the oil price lower than the natural gas price. Okay. Let's wait a bit that the optimizer will read the new value. Okay, you see here now that the optimal load allocation changed because actually what is suggesting us is to maximize the oil boiler on the high pressure header and to minimize boiler 3, which I can tell you now that has a lower efficiency than boiler 2, and I will show you in a while this, and also to still maximize turbine 1, but not turbine 2, which has a lower efficiency than turbine 1, and I will demonstrate you this. And also we moved some of the production from the high pressure header to the medium pressure header because now boiler 5 and boiler 7, they are maximized, okay? So let's go back for a second to see what happens to our cost function. You see when you have a change in the price of raw materials, of course you have a step in both optimal and actual cost of production, okay? And also this bar charts changes because it changes the optimal load allocation. But immediately you see that the blue line is slowly decreasing again because immediately when there is this change, the optimizer is reading the new optimal target and is trying to achieve this new target. Okay, so if we go back here, you will see that we have a change in the production. So we were, for example, decreasing the load of boiler 1, and now we are increasing it because we changed the oil price. And last example that I think it's good to show you is regarding the electricity price, because this makes a lot of difference in our optimization. So let's try the test Ricardo talked about. So when we have a low electricity price, since now the pressure relief valve was always minimized, but when you have a low electricity cost, it doesn't make sense anymore to use the steam in order to produce electricity. So you see that the optimal allocation for the turbine now is basically 0, but the software is suggesting us to use the pressure relief valve, because you have the attemperator after the pressure relief valve that produces more steam, and so it makes it more convenient, okay? And so we can go back to the monitoring tab again, once again here, and you will see that we have again a step in our cost function, but again the blue line starts to decrease immediately. And if you look here, now that we changed the electricity price, we have the pressure relief valve and the 2 turbines that are very far from their optimal load allocation, but the boiler, they are much closer to the solution, because we didn't change actually price of gas or of oil. Okay, so this is the main idea behind this, but I think I still need to show you a couple of interesting stuff. So let's go to the optimizer settings. So just to give you a small explanation, when I mentioned that we are also taking into account the efficiency. So here we have these 2 coefficients that are regarding the efficiency of the single equipment. Okay, so if you check, for example, boiler 2 and 3, you will see that boiler 2 has a higher efficiency than boiler 3, as I mentioned before. And also, if you check the turbines, turbine 1 has a higher efficiency than turbine 2, for example, and also than turbine 3, which has the lowest efficiency, but in this demo was in off mode. Okay, and last, I think it's still pretty interesting to have a look at the visual representation of the mass balances on the 2 headers, because this gives you an immediate representation of the flows in your system. So basically, we have this Sankey diagram which shows you the steam distribution in your network. So for example, we have the producers on this side and the consumers on this side. So this is the high pressure steam balance. And we also have the same representation for the low pressure, but also for the entire network. So by starting from the feed water on this side till the consumers on this side, okay? And we have high pressure header here, and also we have the low pressure header here. And this gives you a direct representation on if you have any losses in your system, or if you have, I don't know, for example, if you're venting. And so I think this is pretty interesting. And I think these are the main stuff. Of course, we can go a bit into more detail if you are interested, and maybe you can ask us some details for a more detailed overview. Okay, and so we can go back for a second to the presentation.
Thank you, Francesco, for the great demo. As Francesco already said, so we can give you a more detailed demo on the system, and we are also happy to show you more on that.